Good morning, everybody. My name's Steve Olmsted. So what I'll do is try and untangle a little bit of civil integrated management and 2D and 3D and what that meant to the world of a state DOT. I didn't see a huge amount of DOTs at this one. I was contacted to kind of bring a lot of what we're doing, and especially how that relates from a visual standpoint. So you can see some of the photos that we start out with. The area that I work in, I work about half the time in environmental planning, environmental engineering, and the other half for the state engineer's office for Arizona DOT. And we've been after for a couple of years now to do a better job, whether we're talking bridge replacement, scour work, better understanding of our extreme weather events, low water crossings, overtoppings at our roadways, inundations of culverts and the such. So a lot of it is water, but there's a whole bunch of other stuff, especially when we deal with emergencies, that a lot of the visualization kind of fell into. We also started working over the past year with LiDAR and drone, predominantly, photogrammetric at this point. So real quickly, my goal was I actually read the symposium description, and I wasn't sure if I was supposed to do the entire presentation in visuals without any words at all. So I did stick a few slides in here with words so we could at least look at civil integrated management and what that means, especially since it's relatively new. So here's our assets, Arizona on the top, ADOT's assets, but obviously the 30,000 maintenance lane miles we have connect the entire 140,000. We really have responsibility. That bridge number is actually closer to 7,400 now. As a lot of you know, because of the expense of bridges, locals and municipalities use a lot of federal aid money to repair those. So we ended up either administering the projects or at least we're a go-between. The bottom part is the most interesting. Those of you that visited Arizona may know the Valley, but then also Sedona and Flagstaff and the Rim. But our assets operate under some interesting conditions. So I brought pictures. I figured the easiest thing for visualization was the good old picture to kind of give you a taste of at least the outer extreme of what we deal with. And hopefully then by the end of the presentation, you'll see where some of the visualization has kind of drawn us forward out of the static progress meeting where each discipline brings in their PDF sheets, and everybody looks down until they're called on the meeting agenda to speak. So this is a pretty typical dust storm for us. This was a bigger one from 2011. That's downtown Phoenix. Usually we make forest fires along with California. We make the national news. Here's slope erosion. And you can already see where we were mitigating already the slope before, and here's another event that started to erode the base of the slope, and then all the damage around the concrete box culvert. Here's a classic inundation, kind of what we call a cascading effect. That's actually endearingly termed Skunk Creek at the upper right of your photo. That overtopped, spilled down straight to the lower right to a county road, and there was two 36-inch pipes there that obviously couldn't handle it, and it did an end around out onto I-17, and that shuts down a lot of our traffic. Here's a relatively well-known US 89 landslide in our far north part of the state. And here's a extreme flow event, hydraulic failure. In many instances, you can see to the left, the asset actually survived relatively good. The water just pulled everything out around the asset. Geomorphology, I had to teach myself the actual difficulty of saying geomorphologic. Took me about a year or two to actually get comfortable saying in presentations. These boulders, it was almost like Fred Flintstone. They floated about 2 miles from a similar rim that you can see in the right. The rim was actually to the left. Okay, so then just a couple of slides, kind of our visualization. It's actually not a term that I would say we used a lot inside our state DOT a couple of years ago. the idea of digital tools and modeling has kind of morphed that term into our environment. You see the catalyst for some of our efforts. A lot of it was just better conversation pieces, especially on some of our larger or more complex project development projects. Some of you may or may not be familiar. It's a good report on CHRP 831 on CIM. It's got 2 volumes. And then for us, a lot of the asset management, MAP 21 performance requirements really just put the onus on the DOTs to kind of up their game. And then just keeping pace with what a lot of people I think are more familiar with are public outreach 3D simulations. I got a couple of there. I don't think we have enough time to watch them, but maybe at the end in public outreach and planning. So civil integrated management, the areas that we work on at ADOT, if we look at the modeling tools on the left, we're obviously working on all 3. If you look at the data management through the middle, I'll point out for my presentation, it's really kind of the asset management and geographical information systems, GIS, the 2 middle ones. But the big thing is on the right. So airborne, mobile, and terrestrial LiDAR is from a consultant engineering standpoint, those that are on our statewide on-call contracts collect roadway survey data using LiDAR, and they have for a little while. But the idea of us using it in-house for a myriad of asset management, data collection, traditional survey is a little bit newer. So this presentation, the remainder of it, I'll kind of focus on aerial imagery, LiDAR, and if we go down, we obviously do ground penetrating radar. We have big clays that are under our washes that affect the bridge piers, and then the drones at the bottom. So I think this is probably the last slide with words on it, I think, but kind of the civil integrated management for ADOT and the areas that we found visual tools and the use of visualization to communicate is kind of listed here. Some of you may or may not be familiar with much more of the architectural engineering side of things, the BIM. Those advancements have been around for quite a while, and I think some of the CIM is an offshoot of that, and just kind of harnessing digital tools and modeling tools inside, for our case, DOTs. And I'll talk a little bit more about bullet 2, 3, 4, and 5. So 3D land-based, LiDAR, 2D H&H, and 3D engineered models for the rest of the presentation. So those of you I think are probably relatively familiar. Those that are not, this is just a little test plot, and then they're processed. And this would be a very basic example of where we could bring this visual tool to a kickoff meeting, put it up on the screen as though we have here, and actually get folks up and out of their PDF design sheets. We actually, about 2 months ago, did a trial run or a mock 2D or 3D progress meeting where nobody was allowed to bring any paper. They were allowed to obviously bring some notes. But we went through with project managers and the outside design engineering firms to kind of actually do a standard work on how a progress meeting would go using digital tools. So here's an example. This is a 1931 bridge on our switchback areas. As if you're familiar with Arizona, it's got the sea level area and then it rises through the rim. This bridge is one of those structures in our system that's through the rim. And in this case, here's some drone. This was at a fixed wing at 1,200 feet. And you can see then the difficulty on this next slide is kind of where I think we honestly have to talk about the benefits of where a lot of these tools get processed. So this was processed obviously into a mesh. We've got a 3D visual land model. I actually had to manipulate it a little bit to get the whole thing in the slide. But so from a discussion point, these things are fine. If we go all the way through toward the end of the presentation, you'll see the 3D engineering design software examples that are obviously much crisper. But when we're looking at pure drone data collection, you know, the idea of what platform to use to process a lot of these things is a lot to be worked out. The other side of it is, what is the processing horsepower of a lot of the design engineer desktop computer to even really work with these types of tools? I lied. Here's one more slide. I won't go through this too much, but we'll move on to the LiDAR side of things. But I think the bottom bullet is exactly what I just talked about. These newer softwares getting, for those that can do it, much more user-friendly, much more, the interoperability is there to allow a lot of importing and exporting of the data sets. Has gotten a lot better, but we're still talking, you know, aligning scans, working with point clouds, a lot of language and standard work ideas that aren't as familiar with people inside state DOTs. So I'll run through some LiDAR data capture that we've done. You can see some severe bank erosion. If you look really closely to the upper right, that's actually was a cattle fence. It's floating in midair if you can make out the green posts. So this was an extensive erosion that was happening. Now, it had been monitored. If you look to the left under the bridge in the shade to the upper far bank of the wash, very close, you can see the little white discs. Those are the old piers from the previous bridge. And scour was part of the initial process when the new bridge went in 2012. But the final decision on exactly what to put in, because the wash was meandering so severely, was difficult. So moving to a LiDAR situation, and here's one of your scan examples of that same photo, allows the project management team to really bring the whole site in-house. You can share, even if you're out in the districts, everybody can, we've got it now to where they're working off single visual tools through shared folders on the project side. Another example, you can see the terrestrial LiDAR, the tripod up on the far bank, and here's what the scan of that looks like. And one more downstream. And I wanted to get in where once you get to these tools, you really start to get to the ability of colorization for you know, the flows themselves, the vegetation. We've experimented with bare earth. We have a lot of dense vegetation, especially forested areas in our northern areas. So looking at what the true terrain looks like adjacent to the structures is important. Again, when you look at some of these bare earth deliverables, again, we start to border on the cartoonish. So there's a difficult integration process still for not only finding the right tools to use to create the visual products, but developing it in a way that actually is user-friendly and actually useful. So one of the areas that I work on is hydrologic and hydraulic program integration on just improving a lot of what's out there. So we'll talk a couple of minutes here on the newer 2D hydraulic design engineer modeling. You'll see the exact same Laguna Creek in our Navajo country in the upper left. The lower left is the equipment, down-facing particle radar. We have a partnership, $1 million 5-year partnership with USGS to spur them to develop, in particular, land-based and wash modeling tools that can feed into a lot of our need on the CIM and 2D, 3D visualization side. And you'll see the process there of the bridge we were looking at where there was the floating, and you'll see the large gabion basket construction that is going through final grade, I think, this week, if not finishing up today. So a couple of USGS products that they provide for us from a visual standpoint, the flexibility of going out and a lot of what we've been doing is whether we do it in-house with our survey crews that have a drone, or we have USGS do it, or we have one of our engineering firms do it. We'll have the ground-based and then the drone. The ground-based will allow us to get in and under and around the piers. The drone will get us the entire area, 500, 1,000 feet up and down the wash. we'll go ahead and mesh those data sets, and it's amazing some of the stuff we're able to do, which I'll talk about in a minute. But a lot of these are fairly obvious. The idea of working with point cloud is relatively new. How do you store it? I will admit right now I have a stack of external hard drives on my desk. For the most part, I have to take them home and open them on my own computer, even though I've got a pretty decent computer. So there's still a huge capacity and data sharing issue. For example, the terrestrial, the ground-based data collection for this Laguna Creek bridge area ended up being about 11 million data points. The switchback Pumphouse wash bridge where we did the drone was 400 million data points. So being able to cull and carve some of these things is a big deal. A couple of the other USGS and ADOT visual tools that we use, we got to the point now where we're really able to kind of model what the 50, 100, 200, and 500 year is going to look through a certain area. One of the difficulties is really we're not to a point where we can extrapolate, model actual flows or kind of model the vegetative state. So we can kind of do some assumption-based with where the vegetation currently is in the wash. So it's not an exact science, but again, from a visual standpoint, to be able to bring some of these tools into the project development progress meeting is really valuable. I would be remiss, Federal Highways would probably not be happy if I didn't mention their change program. And the bottom, you can see what that stands for. It's really advancing collaborative hydraulics. So there's a new software. It's 2RH2D. It was a Bureau of Reclamation developed software that FEMA adopted and now Federal Highways is using, and this is one of Federal Highways' everyday counts. Again, there's HEC-RAS 2D. There's a lot of different processes in which you can go through. They're trying to create a little bit more of a ubiquitous format. So let me talk about what we were able to do on kind of the fancier side of things. This is a tool that took about a year to develop with USGS. So this is the first attempt, and what we're looking at here is the bank, and I'll go back real quick. This bank in the upper left, and then a little bit out of picture to the right. So you're looking down across at that far bank. So it's not very visually friendly. But what we were able to do was, prior to construction, during stage 1 and stage 2 design, was after there was each event, I sent USGS back out there to do a LiDAR scan, and they were able to then capture the current condition of the slopes and overlay those. The dark red is identified at where the greatest amount of bank erosion was occurring. This is a process of 3 separate post-flow scans mapped into one. So this is the not as visually friendly. So then here's our second attempt. So you can see by having the drone work, capturing from up top, being able to do the ground-based scanning down in the wash. These are the 3 events mapped into one and then overlaid into the 3D meshed model. So what you were looking at during the final grade construction photo I showed you of the Gabion baskets that's the actual design sheet. So you can basically see what you're looking at is the left side, the north side of the bridge, and the left side curvature is where the bulk of that red exists, okay? And then you can see, obviously, that photo I showed you is finished product. So it's one of our very first efforts where we took science and technology, modeled it, worked with the design team. We didn't change design. A lot of these things were already baked in the cake, but we wanted to test kind of a proof of concept to see the alignment of the gabions relative to that erosion change mapping. So I'll just finish up here. This is obviously very straightforward for those of you that work with CAD or MicroStation on the 3D side. This is a Pinto Creek Bridge. It's severe grade slopes in one of our mining areas. This bridge is quite old and it's up for replacement. So this has also been a lot better, again, where the design teams can come in and work off something from a visual standpoint. Here's the same bridge, and again, this was captured by drone as well, by a consultant firm. And you can see the 30% plans there in green overlaid onto the bridge. So I think to finish up, I kind of wanted to go all the way a little step further through the 3D engineered models and software to give you a couple of more examples of where we're using some of these. Obviously, subsurface utility, SUE, roadway engineering, structural engineering, geotechnical engineering. What you're looking at in the upper right is the idea of where you can see column settling for bridges. One of the next pilots we have for the fall that I'm undertaking is our rock slide change mapping. We have 20 or 30 sites on our system, so that's the picture on the lower right, of where we know there's pretty regular movement and activity. The hardest part is obviously the higher elevations of what it looks like at the top. So we're going to mix between doing mobile LiDAR where they just run down maybe every quarter. I haven't quite worked it all out yet, or where we're in less populated area, which most of these are, we can do a drone flyover, just looking for the most cost-effective way to monitor our more severe rock slide areas and figure out a way to better prioritize those in our 5-year program if we need to move them up or back and the such. And this is just the last thing is obviously it goes full circle from the first slide of being able to do 3D animation. I won't play that video, but it's basically where inside, CAD and MicroStation, we have these opportunities to develop the fly-through mechanisms. And we found, obviously, the public loves these things. Unfortunately, they're incredibly expensive. On our larger projects, certainly we wouldn't do it on a small bridge project, but on our big corridor development projects, it still remains a fee or a cost that our director's office generally will approve, because those add-ons can be quite expensive from a public outreach standpoint. So just to finish up, I basically wanted to go completely the other direction from an aerial mapping or GIS standpoint. So we have a huge extreme weather and climate data downscaling effort that we've been working on with Federal Highways since 2014. We're in the process now over the next year of downscaling the remainder of our entire system out to 2050 and 2100. But just to give you an idea of just some very basic colorization mapping, you can look at the left. I can bring that list to an executive decision maker meeting, or I can just bring the map on the right. Same thing here. How do I even begin to discuss the data sets and the process of downscaling climatic scientific information? So developing as user-friendly visual charts and maps that can help kind of compartmentalize the information is helpful. And then just a real plumbing slide was we were in, and I'll give our consultant a lot of the credit, we were faced with wanting to do, in our first climate data downscaling effort, about 30,000 square miles. It would have cost us hundreds and hundreds of thousands of dollars to do that, but we ended up working out a batch process in our script. But in order to go around with Federal Highways and the other DOTs and a lot of the scientific community and discuss, exactly how we did that, this was kind of one of the visual tools that we came up with to communicate those that obviously in the design engineering side would really have no interest or understanding from a software data processing slide. And then the last slide, this has been a long road trying to work through the idea of blending, the second bullet there, blending risk, technology, science, and engineering. Visualization tools have been a big part of that. That wasn't what we set out to do. The idea of adopting and introducing a lot of this language to the design engineering environment was our first goal. Looking for actual 2D and 3D tools to integrate and where there was value and they were cost-effective contributors to project development was important. Visualization just ended up being a great byproduct of a lot of these things we were doing. Obviously, proof of concept through every one of these, we've kind of had to chip away at doing a pilot, talking about it, learning about it, developing some standard work around it, and then writing the 1 or 2 page summaries on how much value there was. And then really how to integrate all these things, obviously from a technology architecture standpoint. But like any DOT does, we have a $1 billion annual construction program. So doing lessons learned and best management practices is pretty imperative because, as we know, especially in even our older states on the East Coast, the cost need is pretty impactful.
Question.